fundamental theorem of algebra says that every polynomial in general form, p of x is equal to an x to the n plus an minus 1 for as many terms as necessary, with complex coefficients an minus 1, a1, a0, has at least one complex zero. And what this means, what this is saying is that if we have a polynomial in general form, if we include complex numbers, then every polynomial has at least one zero. Because in the past, when we've been dealing with real numbers, we've gotten polynomials that had no solutions, that had no real zeros. But the key word is real zeros. If we include complex numbers, then those polynomials now have at least one solution according to the fundamental theorem of algebra. And you might want to know why that is, and the answer is I can't tell you, because you don't know enough math. The only proof I know for the fundamental theorem of algebra is a linear algebra proof, and I'm aware of at least two different calculus proofs, although I don't know them offhand. And I don't even think that there is a algebraic proof. There may be, I don't know, I've never heard of it, but this, you're going to find that the fundamental theorem of algebra has absolutely nothing to do with algebra and has everything to do with proving whether a set of numbers is algebraically closed or not. It just has absolutely nothing to do with algebra. So don't really worry about it. All you really need to know about the fundamental theorem of algebra is that from it we can prove that, even though I can't prove it to you right now, if I can find an algebraic proof for it, which I don't think there is one, there may be, I've never really bothered to look, but if there is one and I think I can explain it, I will try my best to explain it in a way that someone in a beginning algebra class might at least get a semblance of what it is being said. But the general idea of it is as follows, that if we include complex numbers, numbers such as I, minus I, 2 minus 3I, if we include these numbers, because before we've only been including real numbers, such as 1, 1/2, square root of 2, minus square root of 3, stuff like that. We've only been dealing with these numbers. And if we only include these numbers, then equations such as f of x is equal to x squared plus 1 don't have a solution. But if we include complex numbers, what this is saying is that it has at least one. It's saying that every polynomial in this form must have at least one zero. And the whole point of the fundamental theorem of algebra is not really anything to do with algebra, really. It has to do with this whole at least one complex zero thing. And what it's going to do is allow us to prove the following theorem, which is what we are going to be talking about from now on. The factorization theorem for polynomials, which says if a polynomial p of x is a complex polynomial of degree n is greater than or equal to 1, which means that it's not a constant function like x is equal to 3 or x is equal to 4. That means that it's at least degree 1, like x minus 1, x plus 2. So if it is not a constant function, if a polynomial is of at least degree n is greater than or equal to 1, it can be factored into n not necessarily distinct linear factors in the form of p of x is equal to a times x minus r1, x minus r2 for as many terms as we have n's, where a, r1, r2 to rn are complex numbers. So again, we're talking about complex numbers. If we are dealing with complex numbers, it's saying that any polynomial can be broken down into linear parts. So if I have a function of the fifth power, an x to the fifth, what this is saying is that if we include complex numbers, it can be broken down into 5 linear functions. X minus some number, x minus another number, x minus another number, x minus another number, x minus another number. That's what this says. And I'm going to prove this to you, but in order to prove this, what we need to have talked about, and which we have just talked about, is just the fundamental theorem of algebra. The fundamental theorem of algebra will prove this. So what it's saying is that, let's start with the proof. It's saying that if we have some function p of x, that we can break it down into linear parts. So first we have our function p of x, and we are dealing with complex numbers. And now when I say complex numbers, don't get confused in saying that every single number is going to have an I in it. Complex numbers include numbers 2, 1, 1/2. It includes regular integers. All complex numbers means is that it could possibly be like an I or a 2i or something like that. So I hope that doesn't confuse people, because I often hear that it does. That sometimes when someone says, here's complex number, it means that it has to be something with an I in it. That's not necessarily true at all. 0 is a complex number, 1 is a complex number, 2 is a complex number. It just doesn't happen to have an I in it at the moment. So we have some function p of x, and according to the fundamental theorem of algebra up here, it says that it must have at least one complex 0. So that means we can pull out a complex 0, x minus r1, where r is a complex number. Could be a 1, could be an I, could be anything. So if we factor out a 0, then we get a linear factor and some quotient. I don't know why I put a p. Call it q1 of x. And I hope everyone remembers what a quotient is. I hear some people who don't really remember what that word is. A quotient is, let's say if I divide 2 into 10, 5 is the quotient. And basically what I'm writing here is 2 times 5, the factor times the quotient. So I've factored out R1 according to the fundamental theorem of algebra, which says that this must have at least one complex 0. So I've factored out that complex 0, x minus R1, R1 being my complex 0. And I'm left with x minus r1, which is our factor, our complex 0, times q1, which is the quotient of x, whatever's left. But now, according to the fundamental theorem of algebra, q1 must have at least one complex factor. And q1, well, let's talk about what's happened first. q1 is going to be 1 degree less than p of x. If we factored out 1x, that means, let's say that p of x was, again, x to the 5th. That means q1 would be an x to the 4th, because this is an x to the 1st and we factored out 1. So let's write that over here. q1 of x, the degree, is equal to n minus 1. So this is 1 degree lower than p of x. But according to the fundamental theorem of algebra, q1 of x also must have at least one complex 0. So we'll call that r2. And now we're going to be left with quotient 2. So q1 has at least one complex factor. But now, I hope people see where we're going. Well, let's write this too. q2, the degree of q2 of x is n minus 2. Because q1 is 1 degree less than p of x, that means q2 is going to be 1 degree less than q1 of x. But now q2 of x also has at least one zero, one complex zero. So q2 of x is equal to x minus r3. So we've taken out its complex zero, and now we're left with q3 of x. And we keep going and going until we are left with nothing but linear factors. So if this was an x to the fifth, then we would keep going all the way until we had 5 linear factors. So we can write this out in general form. Let me pick a different color. P of x is equal to a x minus r1, x minus r2, x minus r3, all the way until x minus rn, where n is the power of the function. So that means that we're going to have n linear factors. That means if we have some polynomial x to the n, it's going to have n zeros in the complex number plane, or n linear factors. Before, when we were dealing with real numbers, like if we had x squared plus 1, this had 0 real solutions. But in the complex number plane, we get x squared is equal to minus 1, x is equal to plus or minus the square root of minus 1, and the square root of minus 1 is equal to I. So that means that that is equal to x minus I, x plus I. So we were able to break this down into linear factors. And that's all that this factorization theorem is really about. It's saying that when we're dealing with complex numbers, we can break down any polynomial into n linear factors, n being the power of that polynomial. And from here on out, we're going to be doing the same thing we had been doing, except for now we're going to be dealing with complex numbers, where we are going to have i's, 3 plus I, and stuff like that. And we're going to learn about the conjugate pair theorem, and that will explain a little bit more about the nature of the zeros that we're going to be dealing with.